Hello all, warm greetings. So here is the minor project titled The Implementation of Single Point Positioning, that is SPP, and the study of Kalman filter for NavIC receiver, which is prepared by myself, Viraj Makad, and my project partner Sanika Joshi, both students of Bachelor of Technology in Electronics and Communication Engineering at the Institute of Technology, Nirma University. This project is prepared under the guidance of Dr. Sachin Kachchar, Associate Professor at the Department of Electronics and Communication Engineering. So here is the presentation outline, which is the overall flow of the minor project, which would include the prologue and the objective and motivation behind taking up this problem statement. Then it would include the whole project timeline in a Gantt chart format. After that, there will be a certain literature review which would guide to the concept of GNSS and IRNSS. Mainly, this project is dealing with the Indian Regional Navigation Satellite System and the receiver, that is NavIC, associated to it. So there are different topics related to NavIC, receiver positioning, some triple P implementations, that is precise point positioning, significance of Kalman filter, its working, etc. Then we would come to the main part of SPP, that is the single point positioning method, which is implemented using LSM, that is the least square method, and how the program analysis is done. Then there will be a demonstration followed by conclusion, futures prospects, and the references. Here is the prologue for the project. So, as stated, the satellite communication generally deals with the receiver and it depends on various parameters to have a proper communication establishment. So, there is temperature, pressure, satellite orientation, receiver orientation, etc., which play a major role. And there is a specific concept involved for satellite based receiver positioning system. So, there is a certain receiver on ground, that is on Earth, and it is positioned or modeled by removing the erroneous factors. So this technique is SPP or the single point positioning, and it is implemented using LSM, that is the least square estimation method, just so as to estimate the position and have a fruitful communication between satellite and the receiver. So here there are two entities for the project. One is satellite and is the receiver. Satellite communicates with the receiver and gets the data, while receiver that receives data with specific parameters, and it can be velocity, acceleration, pseudo range, etc. Now, this data format is RINEX, that is Receiver Independent Exchange Format. That's a specific format for satellite data. And further on, there will be the mathematical analysis on this file format, and all the results would yield to a final range, and the exact position of the receiver would be plotted in math with the specific coordinates. The main objective for this project was to study GNSS, IRNSS, GPS, NavIC receiver, and the different positioning systems. Also, one of the main objectives was to implement the SPP, that is single point positioning, for the NavIC receiver and study the various Kalman filter properties and applications. Also, from study, it was found that this system is widely used in maritime navigation as it does not require a reference station. So it is very important to have a proper accurate position of the receiver which is stationed at Earth. And the combined effect of the global level, that is GPS and IRNSS, was a strong motivation for taking up this positioning project. Also, SPP is used widely to reduce cost and time due to its optimization. And as in today's world, the aim is to make things as economical as possible. So it was chosen to determine the accurate position of NavIC receiver using SPP and the LSM methods, as the IRNSS need arose due to the advancement in GPS orbit and clock data systems. So here are the four basic problem statements that were defined in order to accomplish this project. The first one is to understand the GPS data visualization, that is the path tracking and coordinate identification. Moving on, the next is linear Kalman filter and its implementation for triple P using two softwares called Python and MATLAB. The third one is about exploring different applications of the Kalman filter. And the fourth one, which will be the final implementation of the technique SPP, that is single point positioning using the least squares estimation method for the NavIC receiver. Here is the Gantt chart, which specifies the project timeline and how the project was carried out. So this project was divided into 4 different phases, and the first one included the study of satellite positioning methods, GPS, IRNSS, etc. Next one included the literature review and to study GPS path tracking and the basic introduction to Kalman filter. The third phase covered the implementation of Kalman filter, its basic understanding for two techniques SPP and triple P, and how the simulation is done in Python and MATLAB. The phase number 4 included the implementation of SPP using LSM, which was finally done via the RINEX file format with the NavIC dataset, and the receiver positioning with the proper coordinates were obtained on the map. And the SPP was carried out with LSM in the software Python. Now, to have a good grip on the technicalities of a research project, it is very important to carry out a systematic literature review and know each and every term and concept associated with the project. So, in space age, the first satellite system for high accuracy positioning and navigation was developed by the US Navy called Transit. So all the satellites from the space age or starting from the first satellite being launched were studies which were followed by GPS, GNSS, GLONASS, Triple P positioning system, etc. Also, based on Doppler shift measurements of a signal, the satellite transited with a navigational accuracy of 25 to 500 meter. So this was an initial range of the accuracy. Now, in 1978, GPS was introduced, which was much superior than transit, and its performance was quite good. This was based on ranging measurements, that is specifying different range, and it had a different constellation design, which was not similar to the transit. In 1980s, the USSR launched GLONASS, which was the second fully operational GNSS system. Also, after that, the US, Russia, EU, and China developed their own GNSS and satellites. So these satellite progress followed thereafter. Moving on, India and Japan had their individual RNSS, that is the regional navigation satellite systems called NavIC and QZSS respectively. So since the inception of these satellites, since last 2 decades, there was multi-constellation approach in the triple P techniques. So since 2009, the first real-time service providing GLONASS had precise orbits and clocks, and it was very much available. So there were different authors who proposed a multi-GNSS triple P model using data from the INGEX, that is multi-GNSS experiment model, and the BETN, that is Beidou Experimental Tracking Network. So this involved China, Japan, Russia, every satellite, and every system was identified, merged, and combined in order to find out an optimized way for the multi-constellation approach in the triple P techniques. So this literature review kept on going, and the different data presenters presented a data processing program for GPS for carrying out SPP and triple P. Also, Rudolf E. Kalman gave a new approach to linear filtering and prediction problem. So thereafter it was found that the positioning of any receiver can also be estimated via prediction or filtering the linearity in a particular path of communication between the satellite and the receiver. So such findings were helpful in SPP, and to be run it in the kinematic mode in an urban area. There were decisions made for pseudo range, and such observations were combined with the performance of GPS, GLONASS, and other satellite combinations. And finally, NavIC receiver was chosen for Indian regional navigation system, and it was developed and advanced in such a way that it could have an optimized manner of approach for detecting the precise position of the receiver stationed at Earth. It was found that to eradicate the problem of single point location which was faced by GPS, there was direct interaction establishment with the RINEX file format, and then came into action LSM, that is the least square method, weighted LSM, and the extended Kalman filter approach, which were all used to get the data solution for BDS or GPS single system. So such framework having robust statistics were developed, and gradually with linkage to the reference of global navigation satellite system, the development and advancement in Indian regional navigation was quite possible with the development in NavIC receiver. So here are the two satellite-based positioning systems called GPS and IRNSS, that is Global Positioning Systems and Indian Regional Navigation Satellite System. So to understand the main concept of GNSS and IRNSS, GNSS, which is Global Navigation Satellite System, and IRNSS, which is Indian Regional Navigation, both respectively work on the global and the Indian regional platforms. So it describes any satellite constellation which would provide positioning, navigation, and timing, that is the PNT services on a global or a regional basis. So GPS is the most prevalent GNSS, and we have NavIC, that is the receiver, for the part of IRNSS. They are widely used in marine transportation for accurately determining the position of ships when they are in open sea. So GPS is dependent only on L band, while NavIC has dual frequency, that is S and L bands. So for the application of positioning and error removal, there are different satellite systems which are developed based on regions or maybe countries. So there is GPS on global level, which has broadcast identification, ranging signal, satellite status, etc. And with a modern GPS having space control and user segment for different applications. Also, as listed, there are different systems called GLONASS, CDMA, BTS, Galileo, QZSS, etc., which would improve comparability with respect to GPS, and it would cover different regions area-wise as per the given specifications of respective satellite systems. Now, coming to the heart of this project, that is the NavIC receiver, which comes under IRNSS, and it's owned by the Indian government and it's developed by ISRO. The services provided by IRNSS are RS and SPS. So NavIC comes under a special positioning service, and it's as well a restricted service, and it's for public use, rolling out in a gradual phase. Also, IRNSS was renamed as NavIC, that is Navigation with Indian Constellation, by India's Prime Minister Shri Narendra Modi in April 2016. So, we would need different methods to position the NavIC receiver, which can also be termed as India's own GPS. So, Triple P is the precise point positioning technique, which uses a single GNSS receiver for the precise position determination. So, it is more common in the area of GNSS and GPS, as it does not require base station with known coordinates. Also, Triple P uses the carrier phase, which increases accuracy, and it does not require differencing in GNSS observations. Also, Triple P needs accurate satellite orbit and clock information, which would further lead to the mitigation of orbit and clock errors. So Triple P is generally a wide concept used in GPS and GNSS, while for NavIC, for more optimization, Triple P can be used, or as well SPP, that is the single point positioning, can also be effectively used. The concept of Triple P and SPP for the positioning of NavIC receiver would include Kalman filter and its specific properties. So Kalman filter is a general estimation algorithm that produces estimates of the hidden variables which are based on inaccurate and uncertain measurements. So there is a list or a certain region of uncertain measurements, and from this the position of the receiver would be estimated and a certain region would be fixed. So here the word filter stands for estimation of underlying states, and it works in the format of predict and update. So Kalman filter has two stages. One is to predict and another is to update. And it's the best unbiased estimator. So here there are different parameters and properties involved for the use of Kalman filter. So the smoothing of parameters is done based on error, mean, variance, etc. So the prediction of future system state, which would be based on the past estimation. So there are certain positions of the receiver which is estimated, and the future prediction of a precise position would be then estimated. Also, if a dynamic linear system with Gaussian noise, then there is a possibility that the optimal estimator of that hidden states is the Kalman filter itself. So the significance of Kalman filter is that it minimizes the mean squared error of the estimated parameters. So it's widely used in radar tracking algorithm and radar systems. Also, Kalman filter is used to tackle the measurement noise and process noise as well. So as shown in the figure 2, there is a specific tracking system which would work on the concept and properties of Kalman filter, and the basic kinematics or the motion equation where x is the target's position also involves the concept of Kalman filter, which is used widely in the radar tracking systems. So here is how the Kalman filter works with the concept of IRNSS. So constant signals are sent by the IRNSS constellation of satellites, and the receiver on Earth would get these signals and it calculates its distance from different reference 2-3 satellites to figure out the exact location. So Kalman filter generally works on a Kalman filter model which has observed state, hidden state, and the state supplied by user, that is due to the communication. So there are various parameters involved in Kalman filter like state transition model, observation model, the concept of covariance, control vector, etc. And here the true state K, that is the present state, is evolved from the state previous to it, that is the K minus 1 state. So here the general concept is that a signal would travel to the sky which would be having some errors, and for the smooth estimation of the receiver position, it's very important to remove these errors. So the Kalman filter algorithm would filter out the rough patch or the signal with errors and pass out the smooth signal. So the properties and the elements would be smooth and a proper estimation of the receiver position can be achieved. So this is how the satellite receiver communication works with reference to the distance formula used for the Kalman filter. So here in the Kalman filter model, it can be seen that there are 4 satellites, satellite 1, 2, 3, and 4, having different position coordinates in form of x, y, and z. There is specific capital Y, that is the range or the distance calculated from the receiver, and the receiver also has some station coordinates x, y, and z. And this is how the communication takes place between receiver and satellite through the distance calculation. So here is the introduction for SPP, that is the single point positioning. Here only a single receiver will be launched and the signal will come from as many satellites as present. So the focus will be on the position detection for only one receiver, and there will be many satellites present to give the signal. So it can be in static or kinematic state, and it is used to determine the absolute position of the station. Now, single point placement in general has a very low accuracy than relative positioning. So there are these two concepts of single point positioning and relative positioning, which depends on the number of receivers in the concept of satellite-based positioning techniques. So the least squares method, or LSM, is the technique which is used for adjustment and filtering, and it's a kind of algorithm for statistical and kinematic as well as dynamic GPS data processing. Also, it is used to calculate the receiver coordinates, and the coordinates are obtained from the pseudo ranges of every epoch. So there are different epochs in the satellite communication, and the errors in satellites are reduced epoch by epoch using the LSM algorithm. So there is a parameter called pseudo range through which the LSM is applied to SPP, and the IRNSS would first estimate a position, then a certain range is decided and the observed ranges are compared with the satellite estimated ranges, and in the certain range there is somewhere the exact position of the receiver. So finally the differences between the estimated range and the computed ranges, that is the estimated and the computed values, are taken and the values are required to minimize to get the exact or the precise value of the receiver. So here is the first phase of implementation known as the GPS data visualization and path tracking, which works as per the algorithm shown, that is input map image is given to the geographical coordinates and the coordinates are extracted to frame the image coordinates, which would have the GPS data linkage. The image would finally be scaled and the specific path would be obtained from the GPS records, that is from the data link file, and the final output map would be obtained. So there is a specific GPS data set that has latitude and longitude coordinates, and this kind of input map image is known as OpenStreetMap also. And a specific image region is decided via the conversion of geographical coordinates to the image coordinates. And finally, the GPS data is linked to mark a specific map, or it is also known as the path tracking, which is pointed through the latitude and longitude, and finally the area of focus is plotted on the map. This is the simulation result where the graph between latitude and longitude is framed, and there is a specific region taken near Ahmedabad, and through this region the blue path or the blue line shows the path tracking from the specific linkage of the GPS dataset. So whichever points would match, a blue line would form through those points, and the certain path would be tracked with reference to the GPS coordinates from the dataset file given. So the implementation of Kalman filter using Python and MATLAB is due to the Kalman gain and its related parameters. So Kalman gain has a major role to play in the Kalman filter and its properties. So Kn is the Kalman gain equation, which would involve the concepts of noise covariance and error covariance. That would include the matrix association with noise and statewise correlation in the observation errors for the vertical level pairs. Also, the term Kalman gain is related to the weight assigned to measurements and the current state estimate. So the current state estimate is a tunable parameter which would be obtained from the previous state also. So this estimation here involves the concept of priori estimate and posteriori estimate, which are used for the estimation of solution size for any PDE, that is the partial differential equation, and the posteriori estimate, which would be the unknown quantity estimation, that is in our case is the NavIC receiver position. So these are the simulation results for the implementation of Kalman filter in the MATLAB software. It shows the positions of actual, measured, and estimated values. So the orange dots in the first three graphs can be seen as the estimated positions. The blue dots are seen as the measured values, and the red path or the red dot can be seen as the actual values. So it is a measure of how accurate the measured values are near to the accurate or the actual position, and how far are the estimated position. So there are different estimated positions in the graph, which are the range formation or the range formatted positions. Near to them, there are some measured positions forming a blue path or blue dots, which has to be precise or the exact position of the receiver. So they are very much near to the actual time. And in the fourth graph, it can be observed that there is a very slight difference between the path of real observation and the estimated observation. So it has to be seen that how close the estimated observation is, and it would finally define that how well the Kalman filter has performed in estimating or in providing the final accurate position of the receiver. So here is the program analysis for the final implementation of SPP for the NavIC receiver. This analysis would be carried out in different stages, and the received data set would be with error. So there are different corrections implemented for the same. And the parameters for analysis are pseudo range, carrier phase, Doppler, signal strength, etc. The software used would be Python, Google Maps, and Google Earth, as the final output would be displayed on Google Maps and Earth as well. So it goes through different functions to calculate time values, ephemeris, orbit computation, etc. And the different stages involve library import, CSV file data, reference selection. Finally, after the mathematical analysis, everything would then be converted to the coordinates and the ranging systems. Also, the computer specifications on which the applications are to be run play a major part in the overall program run, and they are also to be kept a note of. So here is the input CSV RINEX file, which is given as an input to the Python program, and it includes satellite value to be 2346. So from a specific constellation of around 7 satellites, 4 satellites of similar data range and the similar values of data are to be chosen for proper comparison of the NavIC receiver position. And in the second image, it can be seen that different parameters like pseudo range, carrier phase, Doppler, signal strength, etc. for a particular set of time analysis, that is calculated as year 2019, month 11, date 5, are provided as an input in the format of CSV RINEX file. This is the general flowchart of the implementation of SPP. And after importing libraries and the CSV file integration, the process is to be started with parameter assignment via angles called alpha, beta, azimuth, elevation, etc. And the file linkage would then be done. The receiver parameters would further be defined and the mathematical equations and analysis process would start. Also, the original parameter calculations are done with errors and the errors are updated and corrected via the Iono-Klobuchar model, which is also an ionospheric error modeling technique which is necessary to create a reliable positioning system. So the errors are then corrected via different parametric equations and the range for positioning, that is the overall range, is updated thereafter. The receiver positioning is then done using the least squares estimation method and the final coordinates are converted to ECEF, that is Earth Centered Earth Fixed format, and via geodetic analysis the distance between 2 points, one as the found point and another as the reference point, is carried out and the final position for the NavIC receiver is taken and shown on the Google Earth and Google Maps platform. Now we move on to the final implementation and the demonstration for the implementation of single point positioning. Here the program can be seen in Python and it will be further demonstrated and the final receiver position would be found on Google Maps as well as Google Earth. So here the program is run and Google Earth platform would open via the medium of KML, that is Keyhole Markup Language file, which is used in geodetic and geographical file location marking. And here it shows the NavIC receiver. It shows that NavIC receiver is here. So this is the Google Earth, the satellite view, and this is Nirma University campus, where this is the PG block. It's written PG block, where the NavIC receiver is stationed. So here is the exact position found. Now this is the Google Maps platform where latitude and longitude of the same are shown, and this red marker shows the NavIC receiver position which is stationed at the PG block at the Nirma University campus. Here also there are some coordinates which are ECEF, the receiver position in latitude, longitude and altitude format. There is one matrix called QLocal which is for the local estimation comparison. There is a parameter of GDOP, that is geometric dilution of precision, which is a common term used in satellite navigation and geomatics. Also, as specified, two positions of KML, that is keyhole markup language, are given for the Google Earth output. And finally, the distance error, that is the reference point and the obtained point and the error between both these points, which would finally determine where the receiver is exactly positioned, is given by the dist error parameter. So the outcome of this work is a full-fledged research paper titled as the implementation of single point positioning SPP and the study of Kalman filter for NavIC receiver, and it covers each and every section and phase of the final implementation and the study of NavIC receiver, SPP, triple P and the applications of Kalman filter as well. So, as seen, the IRNSS is a regional concept while GNSS is a broader scope, and the Kalman filter is relatively quick and easy for implementation and it provides an optimal estimate of the position. It also helps in reducing the noise and the error values. Also, it's used to calculate the unknown variables accurately on the basis of previously known variables. So the final distance error was found to be 12.14 meters and the receiver coordinates in degree format for latitude, longitude and altitude were obtained as 23.12, 72.54 and 16.83 respectively in degrees. So the implementation of triple P for NavIC or the GPS is a strong future prospect which requires data with more optimization. So the SPP can be extended to the level of triple P and the more precise value of coordinates for the receiver positioning can be obtained, as it has been found that Kalman filter is a more optimized way of positioning and data tracking. So the satellites can be many from a single constellation as well, but then the position will be of a single receiver. So the communication protocol of one to one, one to many to one, and many to many can also be satisfied as a future prospect of the work where position of the receiver can be accurately identified. So here are some of the references taken from well-known research papers, books, etc. So myself, Viraj Mankad, and my project partner Sanika Joshi would like to extend our gratitude to Ms. Mahek Vyas, Junior Research Fellow, Dr. Sachin Gajjar, Associate Professor, and Dr. Manisha Upadhyay, Associate Professor, all three at the Department of Electronics and Communication, Institute of Technology, Nirma University, to provide us with their valuable guidance, materials, and all the necessary help in completing this minor project on implementation of single point positioning for the NavIC receiver. So thank you for watching this video, and do subscribe this channel for more such interesting projects by the students of Department of Electronics and Communication Engineering. Thank you very much.